Hello everyone, welcome to this recorded lecture. Although this can never really replace the effectiveness of face-to-face learning in a real classroom, but given the very special circumstances we find ourselves in, let us try to make the best use of whatever we have. So without much further ado, let us get on with the lecture. In the first week after mid-semester, we started with a chapter on the analysis of stress. So let's put that down. In the second week, we went on to a discussion of strains and stress-strain relations. In this third week, what we are going to start is a discussion on the transformation of stresses. So this is the plan for this week. Now, this is a topic which is used by practicing engineers on a day-to-day basis, and even from a non-mechanical engineering, non-civil engineering, non-aerospace engineering perspective, this has some relevance from the point of view that the higher end stuff of these transformation of stresses as well as transformation of strains, which we'll learn later, it has connections with linear algebra, which finds use in almost all branches of engineering. So this gives us really a headway into a really useful, widely used mode of study. So let's try to see what this is all about, transformation of stresses. To really get into the important concept of transformation of stresses, we have to first very briefly recap what we had studied in the first week while discussing the chapter on the analysis of stress. So there we had learned that we had learned the concept of the state of stress. So we'll briefly recap that. So there we had seen, while discussing the concept of state of stress, that if we have a three-dimensional body, let's use a different color here. So maybe red for our axis. So if you have this kind of a three-dimensional body which is acted upon by various externally applied forces, let's say and we want to investigate what happens to a point which is placed inside this three-dimensional body. So let's say a point Q, which is inside this body. So what we did back when discussing the concept of the state of stress was to take first of all a plane which was parallel to the YZ plane. So we'll just name our axis here. So this was X, this was Y, this was Z. So we took a plane which was parallel to the YZ plane and which happened to be passing through the point Q. So it took something like this. So this plane was passing through the point Q, and it cut our three-dimensional body over this cutting plane. And what we did next was to isolate the left-hand side part of this three-dimensional body, which would look something like this. We understand that this is very much an imaginary cut. Our Q is still here. So this plane is parallel to the YZ plane. Now, what we recognized first of all was that we still had these external forces acting outside. We don't see these two forces, the other three forces, because they are acting on the right hand part and we are not drawing that. Now, to balance these externally applied forces that we can see here, this one and this one, we'll need a distribution of internal forces acting on this surface, the surface which has just been exposed. What we did back then, and we're not going to go into the details of that again, we took a very small area around the point Q and we focused on the effective force or the resultant force that is acting on that very, very small area at the point Q, and we depicted it something like this. So this is an internal force. This green colored arrow represents an internal force. Our next step was to take the component of this green colored internal force along the x direction. So we'll depict it here again. And the next thing we did was to take the component of this force again, this internal force again, this one, along this exposed surface on which Q is lying. So we're going to take the component of this force on this plane. So that is going to look something like this. So we understand that this force that we have just drawn, this is lying on the plane that has been freshly exposed, depicted by the red colored boundary. So one of these components is along the x direction and this one is along the plane, but this is neither along the y direction nor along the z direction. And what we did next was to take the component of this along the y and then along the z. So we took these two components. So the original internal force, let's say this is P, this gets expressed in terms of Px and a V this V further gets expressed in terms of Vy and Vz. So what we did after this was to express stress components in terms of this Px, this Vy, and this Vz. And what we said was that the sigma xx would be defined as limit a tends to 0 px by a. The sigma xy or tau xy would be limit a tends to 0 Vy by a, and sigma xy or sigma xz or tau xz is equal to limit a tends to 0 Vz divided by a. Now the most important thing to note here is that all these definitions of sigma xx, sigma xy or tau xy, and sigma xz or tau xz depends very much in the way that we have chosen our x, y, and z coordinate directions. What I want to emphasize here is that if, for instance, we had taken a different orientation of our x, y, and z axis, then the components px, the component py, and the component vz, they would be completely different, even though we would be still addressing the same three-dimensional body acted upon by the same set of externally applied forces depicted by these blue arrows here. So the same three-dimensional body acted on by all the same forces can show different stress components at a particular point if we choose to work with different coordinate directions, and that is a very, very important point. So the state of stress is very much dependent on what kind of coordinate directions we are taking.